These are 3 glasses. The first has 2 ounces of your favorite drink, the second has 5 ounces, and the third has 8 ounces. Your goal is to empty one of the glasses, but there's a catch. You can double the amount in one glass by pouring from another, like this. Can you empty a glass using a sequence of such doubling pours? If so, how about for these bigger numbers? What if the amounts were any whole numbers? In this video, we'll solve that problem. It stumped 99% of the top college students on the Putnam, a famously hard test. Near the end, we'll look at how many pours are needed to empty a glass. I'll tell you what's known and unknown about this problem. Are you ready? Let's go. Here's our starting example. 2 ounces, 5 ounces, and 8 ounces. We can double the amount in one glass by pouring from another. In this example, can we pour from the first glass to the second glass? No, because the 2 is not enough to double the 5. The glass we pour from has to have at least as much drink as the glass we pour into. Can we pour the other way around? Yes. What's the outcome? The 2 doubles to 4, the 5 decreases by 2. We could also pour from the third glass to the first, like this. Finally, we could pour from the third glass to the second, like this. We'll assume the glasses are large enough to never overflow. So, what's the problem? Starting with 2, 5, and 8, can you find a sequence of doubling pours to empty one of the glasses? Pause the video if you'd like to think about this puzzle, because I'll reveal the answer in 3, 2, 1. Okay, here's one solution. Pour from the third glass into the second. We get these new numbers. Now pour back from the second to the third. Now pour from the third to the first. Finally, we can pour from the first to the third, or the other way around. And we've reached an empty glass. Yay! How many pours did that take? 4. I've listed the triples here. It turns out that 4 pours is best possible for this example, and our solution is basically the only way to do so. But can we solve a bigger challenge like this one? Can we empty a glass here? I'll let you think about this one on your own. As a hint, 10 pours are enough for this example, and there's basically one way to do so. But even if we solve that bigger challenge, that still leaves the main question unresolved. Suppose we have any whole numbers A, B, and C. Can we always empty a glass? This problem first appeared in a Soviet Olympiad in 1971. In case your Russian is rusty, here's an English translation. Later, the problem appeared on the Putnam competition in 1993. It was stated in pure math terms, but it's the same as our 3 glasses problem. The Putnam is for mathy college students in the US, Canada, and Mexico. It has 12 problems, each worth 10 points, so a student can score between 0 and 120 points. In 1993, there were more than 2,000 contestants. Here are some data points. For instance, to rank among the top 207 contestants, the top 9%, the cutoff was 29 points, basically 3 problems. So it's a super hard test. Among those top 207 contestants, how do you think they performed on the 3 glasses problem? Well, 202 of them got 0 points, no progress. 2 of them got 1 point, and 1 of them got 2 points. Only 2 contestants, 1%, got a perfect 10 on this problem. So it's a tough problem to solve in a time-limited contest. Nevertheless, when we look at the problem in the right way, the solution will become clear. Remember, we have 3 whole numbers A, B, and C representing the amounts in these 3 glasses. We have to show that we can empty one of the glasses by a sequence of doubling pours. We'll divide the rest of the video into 5 parts. The first part is an algorithm, a procedure to create an empty glass. That will solve the Putnam problem. But we'll aim for more. In the second part, we'll look at the time complexity of our algorithm, meaning how many pours does it take to empty a glass. Third, we'll find a much faster algorithm to empty a glass. Fourth, we'll find some example triples that require many pours, no matter which algorithm we use. Last but not least, we'll discuss an unsolved problem about the fastest algorithm possible for this puzzle. You know, one reason I like this problem is that it has levels. The first level is one that a child can solve. We have a concrete example like 2, 7, and 6, and in a couple of pours we can empty a glass. But then if we try to solve the problem for any whole numbers, it becomes a challenge that stumps 99% of college students. Finally, if we ask about how many pours are required, we reach a problem that mathematicians have struggled with. There's something for everyone. Okay, first up is the algorithm to empty a glass. We have 3 glasses, and we'd like to find a procedure that guarantees emptying a glass. What makes the problem difficult is that A, B, and C can be any whole numbers. We have no control over them. Our method will be to solve these 3 specific examples. From there, we'll see how to solve the problem in general. Hang on. 3 examples can't solve a general problem, right? Right. But the tactics we'll discover in solving these 3 examples will guide us toward the general solution. Here's the first example. Do you see any relation between these numbers? The second number is a multiple of the first. Can you take advantage of that relation to solve this example? Feel free to pause the video to figure it out. Here's the solution. We'll keep pouring from the second glass into the first. And we've done it. Let's try the second example. Again, the second number is a multiple of the first, namely 12 times the first. So again, we can keep pouring the second glass into the first. And again we reach, wait a minute, this approach doesn't work. We can't just use the first and second glasses. We have to use the third glass as well. Let's try again. Pause the video to figure out how to solve this example for real. Here's the solution. We'll pour from the third glass twice. Then we'll pour from the second glass twice. We emptied the second glass. Why did that work? Here are the 4 steps. Let's look at the first glass. It always doubled. In other words, we always poured into the first glass. Sometimes we poured from the second glass and sometimes the third. Let's write down those choices. 3, 3, 2, 2. How could we have predicted in advance that those were the right choices? To do so, let's look at the second glass. It dropped from 1200 to 0. How? Well, first it dropped by 400 and then it dropped by 800. In other words, it's because 1200 is 400 plus 800. Or in other words, the multiplier 12 is 4 plus 8. We've written 12 as the sum of powers of 2. Wait a minute. That's a concept we've seen before. It's binary notation. In base 2, 12 is 1, 1, 0, 0. Aha! Reading those bits from right to left explains our choices. A 0 means pour from the third glass. A 1 means pour from the second glass. That explains why our procedure worked. The good news is that it goes beyond 12. Every whole number has a binary representation. In other words, every whole number is the sum of different powers of 2. And so our procedure generalizes. Suppose we have 3 glasses in sorted order, where B is a multiple of A. Our algorithm is to look at the bits of B over A. Depending on those bits, we either pour from the second glass or the third glass. The conclusion is that we can empty the second glass. That's great. But what if we don't have any multiples? Here's an example. How shall we solve it? Let's treat the middle number 1299 as if it were 1200 plus a remainder. Here I've shown 1200 on the left and 1299 on the right. We already solved the 1200, so we'll use the same sequence of pours to make progress on the 1299. On the right, we reach 99, not 0. Let's compare our start state and our new state. Have we made progress? It's easier to see if we sort the numbers on the right. Yes, we made progress. In this round, the smallest number dropped from 100 to the remainder, 99. We can keep going. In the next round, the smallest number will be at most 98, and then at most 97, and so on. Eventually, we'll reach at most 1, and finally 0. Our algorithm works in general. We start with any whole numbers a, b, and c. Assume a is the smallest. After one round, the remainder will be at most a minus 1, then at most a minus 2, and so on. Eventually, we'll end with a 0. In other words, our algorithm consists of a sequence of rounds. Each round will reduce the smallest number. We found an algorithm to guarantee emptying a glass. That's enough to solve the Soviet problem and the Putnam problem. Yay! But we're aiming for more. How much time does our algorithm take? Meaning, how many pours does it take? That's the next part. We have 3 whole numbers, a, b, and c. We'll look at their sum, n. When we pour from one glass to another, the sum doesn't change, so n seems like a natural measure of input size. We'll estimate how many pours we make as a function of n. As a reminder, our algorithm has a sequence of rounds. Each round reduced the smallest number. So there are most a rounds. Since a is the smallest number, the number of rounds is at most n over 3. Each round was itself a sequence of pours, depending on binary notation. Here are the first few numbers and their binary representations. How many bits are in each number? The number of bits in n is basically a logarithm, the log base 2. So now we can bound the total number of pours. The number of rounds is at most n over 3. The number of pours per round is at most this log expression. Therefore, the total number of pours is at most the product, which is at most n log n. That's the bound that's mentioned in the literature. As I was preparing this video, I realized that this algorithm is a little faster than that. Namely, it uses at most n pours. I won't go over the details here because we're about to discover a much faster algorithm. But if you're curious, pause the video to study what's on screen. Let's plot the number of pours versus n. If n is, say, 500, then we'll need up to 500 pours. That's an okay bound, but we can do much better. Next up is the speedy algorithm. What makes our algorithm take a long time? In the example here, we made slow progress in reducing the smallest number. We went from 100 to 99 to 98 and so on, up to 100 rounds. Can we speed up the process? We treated 1299 as 1200 plus something. Why not treat 1299 as 1300 minus something? Here we have 1300 on the left and 1299 on the right. 1300 is a multiple of 100, so we know how to empty a glass on the left. Let's mirror the same pours on the right. We're nearly done. On the left, the final step was to pour from the second glass into the first glass, but that's illegal on the right. That's okay. We'll just reverse the arrow. The smallest number is 1, which is dramatic progress. So, we either round down or round up, whichever leads to a smaller number. The worst case here would be 1250, halfway between 1200 and 1300. In one round, the smallest number would be 50. In the second round, the smallest number would be at most 25, then at most 12, at most 6, at most 3, at most 1, and finally 0. 7 rounds is much quicker than 100. Let's try the same thing with general numbers. By rounding b down or up, the smallest number would go from a to at most a over 2, then at most a over 4, and so on. So the number of rounds is basically at most the log of a, which is bounded by the log of n over 3. The number of rounds is bounded by a log, but as we already showed, the number of pours per round is also bounded by a log. So the total number of pours is bounded by the product, namely the square of log n. This improved algorithm used way fewer pours. For example, with 500 ounces, we make at most 80 pours, not 500. Can we do even better? Or is that best possible? That brings us to our next part. Can we find triples that require many pours, no matter which algorithm we use? Consider this triple, 199, and 199. How many pours will it take? There are 3 choices for the first pour. Here they are. They lead to the 3 outcomes on the bottom. Those 3 outcomes are similar. Their similarity becomes clearer if we sort the final triple. Each of the numbers is near a multiple of 100. At the start, the numbers are off by 1 from multiples of 100. After one round, the numbers are off by 2 from multiples of 100. We can keep going. In the next round, we'll be off by at most 4, then at most 8, then 16, and then 32. These triples are still in sorted order. The smallest number started at 1 and only gets bigger, so none of the numbers is yet 0. The next pour won't empty a glass either. At least 6 pours are needed here. Let's look at a more general triple. We'll start with a triple like 1B, 2B, where B is a large number. By looking at such triples, we can show the following result. For every n, there's a triple adding up to n that requires around log n pours, no matter which algorithm. That's a lower bound on the number of pours. Let's compare our upper bound and lower bound. Here we've got log n squared versus log n. Which is closer to the truth? That brings up our final part. To continue, we'll need a little notation. Remember our starting triple 2, 5, and 8? Early on, we showed that this triple could be emptied with 4 pours. It can't be emptied with 3 or fewer pours. So we'll say that pours of 2, 5, and 8 is 4. In general, pours of A, B, and C is the minimum number of pours to empty a glass starting from the triple ABC. That's the complexity of a triple, but what we'd really like is the complexity of a single number, n. For example, suppose we have a total of 15 ounces. We can split it into any of these triples. We can compute the pours complexity of each of these triples like this. Which of these results will be the pours complexity of 15 itself? Well, look at the worst case, the largest number of pours. There are 3 triples that require 4 pours here. In general, to compute the complexity of a given number n, we look at all the ways to split it into triples and then take the maximum complexity of those triples. For instance, pours of 15 is 4. Let's plot the pours function. The general trend is upward, but there are erratic jumps up and down along the way. Here's the lower bound we proved, and here's our upper bound of log squared. The upper bound looks far off, but the lower bound looks pretty close to the pours function. Actually, if we round the lower bound up to a whole number, it seems to be tight periodically. Let's replace the log squared with a curve that looks closer to the data. 2 log n seems to be an upper bound too. I put a question mark here because we don't know whether 2 log n is always an upper bound as n gets large. So, what do we know and what do we not know? This is the lower bound and upper bound we have proved, and here's an upper bound that we think is true, but don't know how to prove. We can get close to proving this conjecture if we cheat. That is, suppose we allow 4 glasses. Now n is the sum of A, B, C, and D. There's an improved algorithm known in this case, namely, we can empty a glass in order log n times log n pours. That's pretty close to order log n. We think the result can be improved to order log n. Maybe you, dear viewer, can make progress on these conjectures. If you like this video, check out this other one too. Thanks for watching!